Welcome to this explainer. Today, we're diving straight into the absolute, ultimate cosmic speed limit. We'll explore why it forms the very bedrock of our reality and how modern physicists are aggressively trying to break it. I'm incredibly excited to unpack this with you because the speed of light is one of those foundational concepts we all just kind of accept as absolute truth. But as you'll see, the science behind it is constantly evolving and it's honestly fascinating. Let's get into it.
Here's our roadmap for today. First, the universal speed limit. Second, the consequences of relativity. Third, testing Lorentz invariance. And fourth, a variable speed limit.
Section 1, the universal speed limit, defining the fundamental constant of nature. Okay, we have to start right here with this exact number, 299,792,458 meters per second. This isn't just a rough estimate or some ballpark figure we rounded up. It is the definitive, hard-coded speed limit of the cosmos. What's truly mind-blowing is how this specific number literally redefined human measurement. Back in 1983, the 17th CGPM officially redefined the meter. So a meter is now exactly the distance that light travels in a vacuum in 1/299,792,458 of a second. They completely threw out the old standard that was based on the krypton-86 atom. Meaning, the speed of light is no longer just a measurement with an error margin, it is a permanently defined constant that we base physical reality on. To really grasp the sheer scale of this velocity, just look at some terrestrial comparisons. A speeding rifle bullet clocks in around 900 meters per second. The International Space Station, it's blazing around the Earth at 7,660 meters per second. But compared to 100% of Clock, the speed of light, the ISS is basically standing completely still. The gap is just staggering.
And yet, this brilliantly illustrates just how massive the cosmos actually is. Even traveling at this unbreakable, maximum speed limit, space is huge. Sure, light zips from the Earth to the Moon in a mere 1.282 seconds. But the Sun? That takes 8 minutes and 20 seconds. Mars, even at its absolute closest, is over 3 minutes away. And Pluto? It takes light 5.5 hours just to reach it. Section 2. Consequences of relativity. What happens when nothing can go faster?
So, because this limit is absolutely rigid, Albert Einstein figured out that the rest of physics has to get pretty weird to accommodate it. First off, nothing with mass can ever reach c. It's impossible because it would require an infinite amount of energy. Then you got time dilation. As you move faster, time actually slows down for you. If you were cruising at 90% of c, your clock would run at just 43.6% the rate of a clock back home. On top of that, objects actually physically contract in the direction they're moving. Ultimately, this speed limit is the c in E equals mc squared, the equation that permanently links mass and energy.
Now, a quick point of clarification here. Light does actually slow down when it travels through different mediums. In a perfect vacuum, it hits that top speed, 1.0 c. But in water, it drops to about 75% of its maximum. And inside optical fiberglass, it slows down to about 67% of c, which is exactly why your transatlantic internet connection has a measurable 60 millisecond latency. That light is literally taking longer to push its way through the glass cables under the ocean.
Section 3. Testing Lorentz Invariance, the exhaustive search for cosmic loopholes.
You know, scientists, they don't just accept a rule without trying to stress test it. This makes our explainer a bit of a cosmic cold case. To understand the hunt for loopholes, we first need to define Lorentz invariance. This is the absolute bedrock of special relativity. It basically states that the laws of physics, including this maximum attainable speed of light, remain exactly the same for all observers, no matter their orientation or how fast they're moving.
Think of it this way. Standard special relativity says there is no preferred frame of reference. It's like swimming in a perfectly still pool. Swimming in any direction feels exactly the same. But searching for Lorentz violations, that's like looking for a hidden current in space. If space is anisotropic, meaning it has a directional grain to it, there could actually be different maximal attainable speeds for matter versus light, depending on which way you're going.
To find this theoretical cosmic current, physicists are running some extreme endurance tests. We're talking modern Michelson-Morley and Kennedy-Thorndike optical resonators. They're literally bouncing lasers off the moon with lunar laser ranging to look for weird orbital oscillations. They're observing massive, distant gamma ray bursts to see if different energy photons arrive at slightly different times due to vacuum dispersion. They even test ghostly particles through neutrino speed threshold tests. They are leaving no stone unturned. And there have definitely been some dramatic false alarms. You might remember the 2011 opera neutrino anomaly. Neutrinos were initially clocked arriving 60 nanoseconds faster than light. It was global news. People thought we were going to rewrite physics overnight. But, well, upon intense review, it turned out to be a measurement error, literally a loose fiber optic cable. Einstein's unbreakable rule held firm once again. Section 4. A variable speed limit. Radical challengers to standard cosmology. So, we know the speed of light is perfectly constant today. But what if we look billions of years into the past? This brings us to a highly radical concept, the variable speed of light theory, proposed by Professor João Magalhães and Dr. Nyash Afshorti. They suggest that right after the Big Bang, the cosmic speed limit was actually drastically higher than it is today, and that superfast light would have directly influenced the formation of early galaxies at the dawn of time. What is genuinely thrilling about this idea is that it isn't just some philosophical guess. They have laid out a hyper-specific mathematical prediction. They predict an exact spectral index of 0.96478 for the universe's oldest light. As our instruments and telescopes get more and more precise, we are actually getting closer to being able to test this number. It takes this completely wild reality-bending theory and makes it highly testable in the very near future. Which leaves us with this massive, provocative question. If the ultimate cosmic speed limit was meant to be broken, or if it changed in the earliest days of our universe, what other fundamental laws of nature are just waiting to be completely rewritten? It really makes you stop and rethink the reality we live in, doesn't it? Thank you so much for joining me on this explainer today. Keep your curiosity sharp, and I'll see you next time.